Yeah, okay. Sorry, there was some problem with recording to the club. Okay, so welcome everyone to this week's Applied and Computational Math Seminar. It is my pleasure to introduce Yasemin Şengül, who's recently joined the department as the lecturer. So Yasemin did her PhD at Oxford with John Ball. She was then a postdoc in Coimbra in Portugal. Then she had a spell back in her homeland, Turkey, and she's joined the department in the last few months.
Yes.
So we'd like to welcome Yasemin to the school and give her opportunity to present her work. And so it's over to Yasemin.
Thank you very much. Thanks.
And I'll move the camera so that we can see the speaker as well.
Thank you very much. So it's a great pleasure to be here and to give a talk about my research so that you get to know me better. And hopefully we will find a way to collaborate in the future. So today my talk will be about strain limiting theory, which I will give the definition in a minute, but more generally, it is in the context of implicit constitutive modeling. And more specifically, on the other hand, I will talk about strain rate type viscoelastic models and stress rate type viscoelastic models. And I have recently been interested in strain limiting theory, and I will just briefly go through what my contribution has been to the theory, really. It's not working.
Yeah, that should be fine.
Yeah, okay, thanks. Okay, so I will start by telling a few things about implicit constitutive modeling by starting with examples from explicit modeling and implicit modeling. And I will try to give you the idea of what are the advantages of strain limiting theory over classical Cauchy elasticity, etc. And then I will define strain limiting theory as a result of that type of modeling. As I said, I will briefly go into strain rate type viscoelastic models and stress rate type viscoelastic models and get an overview. And finally, I will just say a few words about the comparison of strain rate type models and stress rate type models and try to see the differences and similarities, etc. Okay, so in order to get an intuition about implicit constitutive modeling, let me start with an example in an explicitly constituted material. So in this case, let's consider a spring mass system. And okay, if I don't apply a force, then everything is in equilibrium and nothing moves. But then I want to apply this external force to my mass in the positive x direction, and then it moves in the positive x direction. And at time t, it is in the position x. And when I apply an external force on my mass, there is an opposite force in the spring, which is F sub s, and it tries to pull the mass to its equilibrium, right? If this is the case, then my constitutive relation will be like this. So I can write the displacement in terms of the force in terms of kinematics, as in this case. If it's a linear spring, for example, I can even go further and write F sub x is k times x, where k is a spring constant. And this is the constitutive relation describing my model. And then I use the balance of linear momentum together with this relation to get an ODE. And then I want to solve it. Okay, so this is the basic explicit modeling. On the other hand, if I want to do some implicit modeling, in order to give an intuition, let me take a spring wire mass system. Again, if I don't apply a force, nothing is moving and everything is in its equilibrium, etc. Then I want to apply the same external force in the positive x direction, and then it moves the mass in the positive x direction. Again, there's an opposite force in the spring, which is F sub s, trying to pull the mass back to its equilibrium state, etc. If I increase the external force, then the force in the spring will also increase. I continue increasing the external force, the force in the spring increases, but up to the point when I reach the maximum length of the wire. So after that point, even though I increase the external force, nothing will happen. Nothing will happen to my mass. It cannot move any further, right? So in this case, it is much more sensible to prescribe an implicit relation between the force and the kinematics. And the problem is more challenging now because this implicit relation here might not be, I mean, G might not be invertible whatsoever. So it might not allow me to write the force explicitly as a function of the displacement, as in the explicit case, okay? So it's much more challenging now. What we should remember from this slide, or the implicit constitutive modeling for this talk, is this graph. So I will come to that later in the strain limiting theory, but here, as you can see, this is the force in the spring, this is the displacement. I'm increasing the force, external force, but it increases the force in the spring, etc., up to the point where the maximum length of the wire is reached. After that, even though I increase the force, the displacement doesn't change, okay? So even though the force can go to infinity, the displacement will be limited. It will be exactly similar in the strain limiting theory. Instead of the force, I will have the stress. Instead of the displacement, I will have the linearized strain, okay? But the graph will be the same. So as I have just said, the focus of my talk is a subclass of elastic bodies that are defined through similar implicit constitutive relations. But in that case, in my case, I want a nonlinear relationship between the linearized strain, which I will define in a minute, and the stress. And however big my stress is, it will keep the strain, or the linearized strain, limited. So that is the basic idea that I want. And as I said, sigma will represent the stress in my case, and epsilon will be the linearized strain. So it will be limited even though the stress can go to infinity. In fact, such kind of behavior has been observed in experiments. And before such a theory was developed, people were not able to get a nonlinear relationship between the stress and the linearized strain, for example, at the crack tips of brittle materials, etc. I can't remember the exact references right now, but basically, I will tell you the reference in a minute, where I have a review paper and it tells you all the details. Just for some notations, U will be my deformation. F or W, I use both of them as a deformation gradient. B is the left Cauchy green stretch tensor, but it will play the role of the strain in our case, because we really can't use F as our strain because we want symmetry and objectivity, frame indifference, etc. So B is the right thing to do. And L is the velocity gradient, and D is the symmetric part of the velocity gradient, and it will come into play when I'm doing viscoelastic modeling, because it will have a time derivative of the linearized strain. And linearized strain is, as usual, this one. Okay, so what is strain limiting theory? And why is it important? And what are the advantages of that over Cauchy elasticity? So as we recall, we want such a behavior. We want to model such a behavior. And as I said, at the tip of the brittle elastic bodies, the stress can go to infinity while the strain can be limited. So before such a generalization was, well, this was very well known in even 1940s, okay? But then very recently, it was kind of realized in the context of implicit constitutive modeling. It was not that one previously. But since then, people really started to explain mathematically what is happening that they observe in the experiments. And as I said, yes, in this review paper of mine, you can find all the details, all the references where the experiments are observed, etc. So what we do is the following. What are the advantages of strain limiting theory when we do it in terms of implicit constitutive modeling? So we start with an implicit model. As before. So remember the spring wire mass system? So it is like that. But here I have stress T and strain B. So B will play the role of the strain, as I said. It's the left Cauchy green stretch tensor. So if you want your material to be isotropic, then you have some restrictions, and it gives you this relation between the stress and the strain. You can find this in Rivlin's book, and maybe Spencer also does it. They give you the expression right away. I mean, it's not a big deal, just isotropy. But as you can see here, alpha 0, alpha 1s, etc., the coefficients are not constants. They are depending on the invariance of the stress. So it's a highly nonlinear relationship, as you can see. Okay, we don't want to deal with this highly nonlinear relationship. We will take subclasses of that. But in any case, what we observe from here is that we can write stress T as a function of B using this relation, or, okay, omitting the highly nonlinear terms, you can do that. Or the implicit constitutive theory gives us the advantage that you can write B in terms of T as well in a nonlinear way. So let me tell you the differences between explicit and implicit modeling in this context. So in Cauchy, classical isotropic Cauchy elasticity, what we start with is to write stress as a function of the strain, right? And then, okay, you can have a nonlinear relationship between the stress and the strain. So it can be T is, just take a quadratic relationship. It's a nonlinear relationship. It's very easy, right? This one. But again, the coefficients might depend on the invariance of B. That's fine. If I want to do implicit modeling from this relation, just ignore the highly nonlinear terms here. I can write B as a nonlinear function of T, right? For example, this one. Again, a simple one, a quadratic nonlinearity. The coefficients are depending on invariance. So the implicit modeling gives us this advantage. Once we linearize the strain, which means I will assume that the strain or the deformation gradient is very small in some norm. So I will linearize the strain. If I start with Cauchy elastic explicit modeling, I will get a linear relationship at the end if I linearize strain. If I start with this, I will be able to get a nonlinear relationship between the strain and the stress. So that's the whole idea, basically. So as I said, if you assume that the deformation gradient is small in some sense in a suitable norm, then starting from the explicit model, you can linearize the strain, and B, which plays the role of the strain, will go to epsilon, which is the linearized strain, right? This is really the matrix product, by the way. You will get this. The stress is C times E. C here is a fourth order tensor, and I think it is called elasticity tensor. But equivalently, you can write the linearized strain as another tensor product T, and that tensor is the elasticity compliance tensor, but it doesn't make any difference. In any case, this is a linear relationship between the stress and the linearized strain. If we do the other way around, if we start with implicit modeling, write B as a nonlinear function of the stress, and then linearize B, linearization means, as I said, the deformation gradient is small in some norm, right? So instead of the deformation gradient, we can write identity plus the deformation gradient somehow, which is very small, and then B was FF transpose, so you just multiply it, and it will become identity plus 2 epsilon, basically. And if you do that, then you get this relation. And this is a nonlinear relationship between the linearized strain and the stress, right? So we couldn't get this starting from Cauchy elasticity, but starting from implicit modeling and writing the strain as a function of the stress after linearization of the strain, we can get a nonlinear relationship between the strain and the stress. Okay, so this was really the general advantage of doing this kind of modeling. It has been studied by many authors before in the context of elasticity. What I wanted to do was to do it in viscoelasticity. So many people, including Rajagopal and Sakkumandi, introduced this model just to study responses of viscoelastic bodies, but not in the context of strain limiting theory. Okay, they just wanted to study viscoelastic bodies, and this was a very well established model for viscoelastic response. And then I said, okay, why not linearize the strain in this case and see what we can get, right? And if you do that, here, if you look at this, recall that this is the strain, it will go to a linearized strain, epsilon. This was the symmetric part of the velocity gradient. So it kind of will converge to the the time derivative of the linearized strain because of the time derivative in the velocity. So you will end up with this relation. Okay. Again, the coefficients are dependent on the invariance of the stress. So it is a nonlinear relationship on the right-hand side. Okay, we took this relation because it was well studied before for viscoelastic response. But why not take any other nonlinear relationship on the right-hand side and try to see what happens, right? So at the end of the day, we have the strain and the strain rate. This is what I call the strain rate. And this is a nonlinear relation between the stress and the strain rate. So let's see what happens. So that was the idea. Okay, you always start from the simple case, right? So we looked at the one-dimensional case, which is that one. And we simply take gamma to be 1, which is the coefficient in front of epsilon, but it really doesn't matter. But when nu is 0, it reduces to the elastic case. But this is viscoelastic case, so it is much more general. And be careful that in the one-dimensional case, the linearized strain is just u sub x. So it's just the x derivative of the displacement. Right. So what can we do about this? Is a constitutive relation. So what we should do is exactly what we did at the very beginning of my talk. We should take the equation of motion together with this constitutive relation and try to drive an equation to solve, right? So with my colleague Hüsnü Alterbay in Özyeğin University in Turkey back in 2015, what we did was take this constitutive relation together with equation of motion, we drive this partial differential equation. What we did was just basically, what is the equation of motion? It is u sub tt is t sub x, right, in 1D. So assuming that everything is regular enough, you just take x derivative of that equation and then replace ux by epsilon, right, the linearized strain. But then you can take twice time derivative of this equation and then put epsilon is txx here. So you get this equation basically. It's just a straightforward differentiation and substitution basically. Okay, what is special about this equation is that, first of all, unlike the usual equations that we solve in solid mechanics, it is not in terms of deformation or displacement. It is in terms of the stress, right? So it is not so common. And secondly, unlike the usual equations that we have, the inertia term is nonlinear. Usually what do we have? We have the equation of motion, which has u sub tt, which is linear in the displacement or the deformation. But here it is nonlinear. So it's kind of an equation which is interesting in its own right, I think. And it is very difficult to attack to it because it is nonlinear in the inertia term. It's a dynamical partial differential equation, which is nonlinear in the inertia term. And the unknown function is the stress, not the deformation. Anyway, what we did was to see whether we have any notion of a solution for this partial differential equation for some spatial nonlinearity G. So that is what we did in this paper. So what we did was to look for, so we passed to the traveling wave variable. We obtained some ODEs. That's what you get out of that. And for some spatial Gs, which are here, model A, model B, C, and D. For these Gs, we showed that we can get traveling wave solutions analytically or numerically, okay? I'm not showing you all the models here, but just one of them, which is model B, which is the red one here, because it's the limiting case. And it makes us stay in the context of strain limiting theory because, okay, what was the idea in strain limiting theory? It was that stress can go to infinity, but strain should be limited, right? But here I'm in viscoelasticity. So what I should have is strain plus strain rate is limited when T goes to infinity. So this is really the idea of strain limiting theory in the context of viscoelasticity, and this red model, which is the nonlinearity here, as we see, is really the limiting model. So it's special. Anyway, it was one of the nonlinearities we handled in that paper, but I will come to that nonlinearity later as well. So that's why I wanted to show you. Anyway, we observed that traveling wave solutions exist analytically or numerically for this kind of model. So it was the first thing the first result to get some kind of a solution for that partial differential equation. Also, I looked at the case very recently for the arctangent time nonlinearity on the right-hand side, because it is such a nonlinearity which has been studied very well in the elastic setting, but not in the viscoelastic setting, and it was possible to do that as well. Okay, and then once we get the traveling wave solutions, which means we have some kind of a solution, we looked at the Cauchy problem related to this PDE. So we had some initial data. So this is with Hüsnü Otarbay and Albert Erkek from Istanbul again. And okay, we proved local in time strong solutions for the Cauchy problem. I will tell you more details about that. And recently I obtained global in time solutions for that, but it has completely different approach. So I will not tell you anything about that. I will tell you about how we obtained the local in time solutions for this Cauchy problem. So what we did was, okay, as I said, the variable in the equation is the stress. We wanted to change it in order to get the nonlinearity, get rid of the nonlinearity on the inertia term. In order to do that, we make the change of variables. Omega is the strain plus the strain rate for us. So omega will be the thing that we want to be bounded as stress goes to infinity, right? By doing that change of variables, you can invert, assuming that the nonlinearity is invertible, which seems to be a very restrictive assumption, but it's not, at least in some regions. So it's okay, but not globally. Anyway, assuming that G is invertible, you can write stress as a function of this omega, which is the strain plus the strain rate. And using this variable, you can get rid of the nonlinearity in the inertia term. So this is more like what we are dealing with usually, right? But of course, the right-hand side is terrible. It's nonlinear. Anyway, you can sort out the initial data accordingly as well. So instead of that equation, which was in terms of t, with a nonlinear inertia term, we dealt with this equation, which is in terms of omega, but a linear inertia term. Okay. Okay, it was not enough for us, so we couldn't do anything on the right-hand side. So we had the idea, if we can write this equation in the divergence form, it will be very advantageous for us. And in order to do that, we make another change of variables. So from omega, we went to eta x. And we write exactly the same equation, which becomes this. You can sort out the initial data accordingly, so no problems with that. But what was the advantage of this, writing it in this form, is that you can add eta t to both sides. The problematic term is really this viscoelastic term. It is h eta x xt. So you can take its time derivative like this, and you can write that equation as a system. It is advantageous because what we will do is, okay, so eta t is u, that's fine. But look at the second equation. So it is in terms of u, right? But here g has eta, f has eta, and unfortunately this a also has eta. So what can I do about it? It's an equation in terms of u, but the way that we solve it is the following. So we will treat the second equation as a variable coefficient heat equation. But we can only do this if eta is given. So what we do is, you give me an eta, I will fix it. I will treat the second equation as a variable coefficient heat equation. And I know the solution of that equation. It gives me an evolution system, right? It gives me bounds on u, etc. And then I define a suitable set to recover the given eta from u. So it will be a fixed point argument. So you give an eta, I fix it, I solve the equation as a variable coefficient heat equation, and then in that set, I do a fixed point argument to recover the given eta by Banach's fixed point theorem, basically. So this was the whole idea, and we could only do it by doing that change of variables, really. Anyway, we obtained local in time strong solutions in those spaces. As I said, global in time existence is also done, but I will not go into that now. Okay, one-dimensional Cauchy problem is done. So of course you will think about, how about 3D, right? So with Mira, Vicky, and Andre, we considered this three-dimensional problem. You have the equation of motion, you have the constitutive relation, you want to solve it. What we get was global in time existence of weak solutions in this case, but with periodic boundary conditions and Dirichlet boundary conditions. So it really kind of closes the strain rate case. Three-dimensional problem, global in time existence of weak solutions. So that's the end of the story somehow. Okay, so in those papers, we looked at the special case that I showed you before, which is the red one, because it is really the limiting case, and it really makes us stay in the context of strain limiting theory. And when t goes to infinity, it goes to 1, so it really stays limited. And you can get there. So we started with this relation, remember? And if you put beta 0 and beta 2 to be 0 and beta 1 to be that, which is depending on the invariance of the stress, then you can get that nonlinear relationship. So it was really at the core of the strain limiting theory, which is in the three-dimensional case. And for simplicity, we just took the coefficient of strain rate to be 1. Right. Okay. Yes, so this is just some details, but it was known, so Ito, Koutnenko, and Rajakopal observed some things, they did some analysis on this kind of equations before. Well, this is how I write their equations. They didn't write their equations this way. Okay, they didn't know that they were doing linearized elastic, linearized strain, etc., etc. What they were interested in was to look at the quasi-static case. Quasi-static means you are ignoring the inertia term in the equation of motion. Okay, mathematically it is easier, but and meaningful, of course. Physically, usually what you when you do quasi-static analysis is when your system evolves very slowly in time. So you just neglect the inertia term and look at the equation that way. Okay, so it is the fully dynamical system. It might not capture all the properties of the fully dynamical system. In other words, they use some techniques, some regularization techniques, some fixed point arguments, and we looked at the fully dynamical system. But what's basically the difference between what they get and what we get is they got measure valued solutions, we got weak solutions. And also the basic and the most important part in our work was that the constitutive relation that we had was satisfied point-wise, rather than in a variational sense. So that was the compactness, which was making a lot of problems, but we managed to get that, even in the dynamical case. Okay, so as I said, we looked at the periodic case, periodic boundary conditions and Dirichlet boundary conditions. I won't go into too much details here, but what you do is you really to define what it means that you have a weak solution, what it means that you have a solution, right? This is the constitutive equation. And what we do was to consider a regularized nonlinearity. So the nonlinearity is really the red dot that we consider. This is the regularized version of it. When n goes to infinity, it converges to the one that we want. So what we did was to use to prove existence of solutions for the regularized problem by using a Galerkin method, and then we obtain some bounds which are independent of the regularization parameter, which is n, which means you can pass to the limit in them, and then you can show that the limit is really the solution of the weak solution of the system that you want. As I said, the main difficulty was that to show that the constitutive relation was satisfied point-wise rather than a variational sense. The Dirichlet case is also very similar, just the Sobolev spaces are different, but again, we get unique weak solutions in this case. So this is just the definition of the problem, the definition of the solution, and these are the boundary conditions in this case. Again, we use Galerkin method to show existence of solutions for the regularized problem, for the approximate problem, and then take the limit and then show that the limit is the right one. Okay, so that's the it's really the classical things that we do in three-dimensional problems in PDEs. Okay, so this really closes the case of the strain rate models, if you ask me. but of course, one can have much more general nonlinearities, etc., etc. So you might, one might like to look at those ones as well. But further than that, we looked at the stress rate type problem. So what does that mean? Remember the implicit constitutive modeling that we started with? I had an implicit relation between the stress, strain, and D. And D was the symmetric part of the velocity gradient. So it was the viscoelastic part somehow, strain rate, in other words. Here, instead of that, instead of D, I want to have the material time derivative of the stress. Okay, so this is the stress rate part. That is what I call stress rate. Why not? Okay, let's try and do mathematics out of this. We can. But of course, the question also remains, is it mechanically consistent? Does that mean anything? Anyway, before answering that question, we can take a subclass of this implicit constitutive model, which is this one. In other words, I'm writing B, the strain, as a function of stress, but also the stress rate. Okay. Previously, it was B, a function of the stress, right, in the elastic case. But here I'm adding stress rate as well. Again, we want to apply the isotropy of Spencer or Rivlin, whoever you call it, and you get this highly nonlinear relationship between strain, B, stress, T, and the stress rate, the material time derivative of the stress. Again, the coefficients can depend on the invariance of T and T dot, basically. So again, this is a very difficult relation. It's a highly nonlinear relation. Again, we want to do the same thing. We want to linearize the strain. In order to do that, we assume that the deformation gradient is small in some norm. But also we need to assume that the deformation of the velocity, the gradient of velocity is also small, so that the material time derivative of the stress will reduce to the usual time derivative of the stress, and it makes sense if you assume that as well. So you just neglect the convective terms, and then the material time derivative becomes the usual time derivative of the stress. If you do that, then it means you just linearize your implicit constitutive model, and you end up with the linearized strain on the left-hand side, which was coming from B, basically. And on the right-hand side, you have a function of T and T sub T, which is the stress rate. Of course, it's a very general nonlinear model, and you can have subclasses of that. And you can have this kind of a subclass where you have a separate function of the stress and a separate part where you have a linear dependence on the stress rate. Of course, you can have nonlinear dependence as well, but it will make things more difficult. So this was the first thing that we tried to look at. In fact, we didn't even look at this one. We looked at the case when gamma is just a constant. It doesn't even depend on T. So we have a part which depends on the stress, and we are linear in the stress rate part. So that's the easiest one to start with. And here, what we did in this paper, what we did was to show that it is meaningful. In other words, we can start implicit constitutive modeling by putting the stress rate there, because what we showed was actually to show that this constitutive relation, we can get that constitutive relation starting from Clausius-Duhem inequality using free energy, complementary free energy, and Gibbs free energy. So you can end up with that constitutive relation, which shows that thermomechanically, that model was okay. And also, it was different because we used Gibbs free energy. Usually, Helmholtz free energy is used in order to show that, show this kind of consistencies. What we did was to show that it is mechanically okay. And also we wanted to compare the strain rate type model with the stress rate type model, the solutions of the equations that we get, in other words. So what are the differences? What are the similarities? What one can do is to look at from various aspects. You can look at energy decay, and you will see that they are both decaying the total energy. You can look at from a point of view of nonlinear differential equations of motion. You can do Fourier analysis of the corresponding linear models, etc., etc. And what we did was similar to the strain rate model, this one, we use equation of motion and the new constitutive relation with the stress rate, and we try to get a PDE out of it, exactly as we did before. And you end up with this PDE. Of course, it's very similar in some sense, but also different. Again, it is a nonlinear inertia term, similar to that. It has T sub XX, similar to that, but that was coming from the strain rate. This part is coming from the stress rate, basically. So that's the basic difference. You can do similar analysis for the Cauchy problem. You can try the three-dimensional case, etc. But before that, what we did was, let's have a look at the traveling wave solutions of this. So what do we get? And what we get was, you get exactly the same equations, exactly the same ODE if you pass on the traveling wave variable. So you have strain rate problems and stress rate problems, and they both have, you use equation of motion together with different constitutive relations to obtain different PDEs. And once you pass to the traveling wave variables, you get the same solution. So looking at the traveling wave solutions for the stress rate problem was unnecessary because we already did that for the strain rate problem. But of course, the Cauchy problem, the boundary value problems, they're all meaningful and they are still open. At the moment, we are looking at the more general stress rate type models and try to show that they are thermomechanically consistent. Okay, so that's the end of my talk, and these are further references that I didn't give you within the talk. So if you have any questions, I will be very happy to answer. Thank you very much.
So if anyone on Zoom has questions, please type them in the chat. Thank you.
So it's nice theoretical framework now. So I suppose you aim to apply it somewhere to see how it works for certain materials, because some materials might when it's ready. I think the theory is great that it's there and it's very general, so you can choose those functions.
Yes.
Now it's please and you know what.
Yes, mathematically it's interesting.
No, it's more than interesting. It's also when you
Established, yes, yes.
Captures a lot of aspects. So it's great. But do you have any materials in mind where this is actually
yes
where you can
apply them?
They work?
Yes, well, I don't think that the stress rate, this much details, I haven't seen any experiments which says that, oh, this should be depending on the stress rate, etc. But usually what happens is that material scientists or mechanical engineers do experiments and they have graphs. And by just looking at their graphs, we can only judge whether it is in the context of strain limiting theory, which means when stress goes to infinity. Gunmetal alloys, for example, titanium alloys, these kind of materials. As I said, in that review paper, we have some or soft matter, human tissue kind of.
That's what I wanted to get
yes.
to, actually, it's the so-called chain limiting. Type of models to get models.
Chain limiting?
Chain limiting. And the chain limiting is exactly, so what it's doing is that the stretch,
yes,
if you're just talking about
that's fine. Yeah.
The stretch is limited.
Okay, that's fine. Yes.
So
yes, exactly. That's okay.
That's starting with the elastic case. So I believe one with especially about because the model is used for.
Yes. Yes, absolutely. Yes.
And there's also more recent models, it's a Hookian type, and there's loads of papers now they start coming to because they're trying that model in different kinds of deformations, this shell inflation and so on. They just try to see how the model performs.
Neo-Hookian type, I don't know.
No, but that would be interesting.
But maybe it is applicable.
Can be, I don't think so. Maybe I should show you where.
Yeah, okay.
Well, there are more than two, but there is a recent one, and it's the classical get exhibit chain limiting. But is the more recent one.
Yeah, soft tissue, etc. That experiments also have similar graphs, so they fit in the context of strain limiting theory. And I think chain limited, you said, right? I think in 1940s, this behavior was kind of recognized by Prager, but he didn't call them strain limiting, or I think he called them locking materials or something like. So the idea was there somehow, but he didn't realize that you can get a nonlinear relationship between. Maybe that was the chain limiting was also similar to that. So one needs to check, but certainly many materials. Yes. Yeah.
At the beginning of the talk, we were talking about ways in which models could limits on the spring extension.
Yeah.
So there's a similar problem in terms of viscoelastic difference.
Okay.
Model the polymers
Yes.
So,
explicit versus implicit, you mean, right? Yes.
Right. So it could be interesting to look at whether your work could be applied
Yeah.
in that context.
Yes, in the fluids, they also did some work. This Rajagopal and his colleagues did some work in the context of fluid mechanics, and they don't put D for the viscoelastic case as we did as a variable, but something else, probably coming from other notions in fluid mechanics. I don't really recall, but they do exist already. I mean, elastic setting, not in the viscoelastic setting, I would say, but they somehow do. This is more solids. The elastic setting is more solids, but they did some similar stuff for fluids as well. So yes, it already exists actually. But maybe for viscoelastic case, one can generalize them to other by starting from scratch with different implicit constitutive models and then passing through the linearized case. Yes, certainly.
And the second question is that you developed some very nice theory for the strain rate models and for stress rate models. Talk about the next step in combining this.
Combine them? Yes, you can put them together. Definitely, you can put the strain rate and stress rate together, because once the stress rate is thermomechanically consistent and strain rate as well, you can have. But I don't know whether there is a material which shows both behavior response. I mean, but mathematically it is of course possible, but it will be much more difficult to handle all these nonlinear relationships, and certainly you will have to go to ignore some nonlinear terms and pass to the subclasses anyway. But yes, it is possible, at least starting from a very simple strain and stress rate type model together will be a different point of view, I think. Yes.
It could be one way of passing the whole spectrum of this kind of
Yes.
solid.
Yes, exactly. Yeah.
I just have one question. So you mentioned how in the stress rate model end up with the same term.
Yes.
Was it a surprise to you, or I mean?
Well, I don't know. If you can just have a look at these two equations and pass to the traveling wave variable on your head, but
Underlying reason why that's something in think or I don't know.
no, we thought they are completely different kind of response, strain rate and stress rate. So, but passing to this kind of PD kind of shows you that they are similar, but also the main issue, the main ingredient is these terms, right? So, of course, yes, if you can do the calculations in your head just by looking at these equations, you can tell me that once you pass to the traveling wave variable, they are the same. I can't see it from the top of my head, but we were not expecting that because, as I said, they are completely different responses. So why would they have exactly the same ODE for the traveling wave variable? But once you pass to this PD, I think it's not so difficult.
Yeah, but there's no any
As far as I know, no, because looking at these two constitutive relations, how would I just see that they have the same solutions, right? I don't know. At least for me, it was a surprise, yes.
Based on Dirichlet and Yasemin. Very nice book.
Very welcome.
Okay, so thank you for coming this week. Next week we'll have Angela giving a talk in person again. So we're continuing with the in-person seminars, and yeah, I'll send an email about it soon, and see you all next week. Thank you.
Oh, great, finally.